We warmly welcome you to day 3 of the ATAL Online Faculty Development Program.
We sincerely thank you for your continued enthusiasm and active participation. Today's sessions will focus on advanced fabrication insights and design automation, further strengthening the link between manufacturing technologies and semiconductor design. My name is Krishika.
And my name is Shivam, and we are delighted to invite you to be part of the third day of the ATAL Online Faculty Development Program, which brings together academia and industry experts to share knowledge, insights, and emerging perspectives in the field of semiconductor technologies. This faculty development program is a pivotal initiative in the context of India's rapidly evolving semiconductor landscape, which is poised to emerge as a global leader in chip design, manufacturing, and innovation. As India strengthens its semiconductor mission, developing a strong understanding of technologies spanning design to packaging has become essential.
FDP offers comprehensive exposure to critical areas such as clean room technologies, vacuum systems, and semiconductor fabrication processes, including lithography and etching, along with advanced topics like EDA tools, AI and machine learning applications in VLSI, and the complete design flow from RTL to GDS2.
In addition, participants will explore semiconductor packaging, nanomaterials, and analog and mixed signal VLSI design, gaining insights into both foundational and advanced aspects of semiconductor engineering.
Through expert led sessions on global market trends, India's semiconductor assembly and testing ecosystem, and emerging industry developments, combined with interactive discussions and practical insights, this FDP aims to strengthen research capabilities, teaching excellence, and industry collaboration, contributing meaningfully to India's vision of self reliance in semiconductors. It is now our proud privilege to welcome our first speaker for day 3, Mr. Shubham Jain. He is the Chief Technology Officer at EDA Librarian, a former Principal Software Engineer at Cadence Design Systems Noida, and a proud alumnus of the North Cap University.
With extensive experience in VLSI and CAD design, Mr. Jain has made significant contributions to the field of electronic design automation. His professional journey reflects strong expertise in industry standard design tools, design workflows, and practical challenges associated with large scale VLSI and CAD systems, offering valuable industry insights to academia. The topic for this session is EDA tools and design automation. Participants will gain valuable insights into VLSI and CAD design methodologies, commonly used EDA tools, and practical aspects of the design flow.
Drawing upon his rich industry experience, Mr. Jain will help us understand how VLSI and CAD design practices are implemented in real world environments and how design tools support efficient and reliable chip development. The chat box will remain open and the Q&A session will be taken at the end. We now invite Mr. Shubham Jain to kindly begin the session.
Hello everyone, am I audible?
Yes, sir, you're
Yes, sir.
audible.
Yeah. Thank you for the introduction. Let's not waste any time and let me share my screen with you. Let me know when you are able to see my screen. Just a second.
Yes, we were able to see.
Yeah, I was doing something. Just a moment. Okay. Yes. Magnify slide. Full screen. Yeah. So which slide are you able to see now?
Sir, the title, the first slide. What is EDA?
Got it. So yeah. So as mentioned, the topic for today's presentation would be EDA tools and AI-driven design automation. So I incorporated some AI details as well for today's presentation because this is the leading buzz in the industry, and we are currently catering to this domain as well. So yeah, so currently I am Chief Technological Officer at EDA Librarian, as mentioned. And previously, I worked with Cadence for around 10 to 11 years, and I resigned as when I was principal software engineer. So yeah, so just a brief. I think all of you must be knowing what EDA is, but just a brief for the people who do not know what EDA is. So there would be few slides relating to what EDA is, and then we will move on to straight the implementation details. So EDA stands for Electronic Design Automation. So if I explain briefly and in a simple terms in a layman's language, whatever hardware you currently see, be it mobile phones, be it televisions, be it your laptop, your mouse, your refrigerator, everything has a PCB in it, printed circuit board. So in those, so that green color plate that I think most of you would have seen. So that is a PCB, and in that PCB you would see black color plastic boxes which are pasted on those green colored plate. So the whole EDA revolves around those black colored boxes and that PCB. So we create softwares that enable electronic engineers, or you can say design engineers sitting in companies like Qualcomm or MediaTek, to develop their processors, to develop their chips. So we basically develop a software that enable them to develop their hardwares. So these software in deals in every domain, like uh, uh, so this there are different domains in electronic design automation as well. First is design, next is simulation. We will briefly cover each of them. Next is optimization, then is verification, and then is manufacturing. So design covers the top level RTL design. So basically what we do here is we use languages like Verilog and System Verilog to basically tell the engine the intent, what I want to do in a behavioral language. It also deals with top level circuit capture. So in digital side, we use Verilog and System Verilog. In analog and mixed signal side, we capture the design signal. We capture the design as part of circuit. So this is it. As just a moment, I need to give me a second. I'll be back. Just a moment. I think my daughter has some problem. Give me a moment. Yeah, really sorry for the short interruption. Yes. So yes. So yeah. So am I audible?
Yes, sir, you are audible.
Yeah. So yeah. So I briefly explained about what the design flow is. So when we cover the digital side, we use RTL design, and when we come to analog and mixed signal side, we capture the circuit in form of a circuit diagram that is captured in tools like system capture, the cadence tool, where we have symbols for each and every chip, for each and every block. We place them on a canvas, a drawing canvas, and then we basically do some circuitry around that, and this is the front end part of it, and then we move to back end where the whole floor planning is done. Next, coming to simulation, basically what we do here is use KCL, KVL in basically I'm explaining in a layman's language. So typically we use KCL, KVL when we come to analog and mixed signal side, and use DSP techniques when we come to the digital side. Next part is optimization of the design. So this is where the design optimization is done. So let's assume you captured the intent in a behavioral language in Verilog. This is where the RTL to to net listing to logic synthesis is being done, and during that the design is optimized. Let's say if earlier we were using 10 NAND gates or 10 NOR gates, this would be optimized to some 4 or 5 NOR gates, or something like that. Next is verification. This is the most trickiest part, and most of the time in the cycle of a chip, in the design cycle of a chip, is being invested in this verification domain. Basically, we use timing analysis and other techniques to verify the design. Typically, we use system Verilog to write test benches for this operation. So basically, we have a Verilog code which is to be tested, and we write a test bench around that Verilog code, which is basically testing that inner block which has the Verilog code. So this is typically the verification part. Next is finally the fabrication. So after all the validations are done and the designer is comfortable to say that this chip would work 99% of the time, then only we will go for manufacturing. Otherwise, this manufacturing is a costly process. Uh, you cannot basically go cycles. You cannot go in cycles to test your chip. So this is the main important part of EDA. Every simulation, every validation is being done on a software, and only after these validations are done, these verifications are done, the whole after the whole design process is done, we finally go for manufacturing, where the fabrication is done. So GDS2, if I say so. Next, we will briefly talk about the evolution of VLSI design and EDA tools. So I briefly mentioned that when we are dealing with analog part or mixed signal part, we place blocks and do some circuitry on a canvas. So earlier, this whole process used to be done manually on a drawing sheet, because earlier the chips were not so complex. So as the time progressed, the chips are becoming more and more complex. So we needed some automation to be done. So that is when EDA tools came into picture. Next, also we had significant breakthroughs in spice simulators, logic synthesis, and physical design automation. So when I talk about breakthroughs, first of all, let me explain you what spice, basically a brief of what spice is. Spice stands for simulation program with integrated circuit emphasis. So this basically deals with mathematical simulation of circuit device level of circuit device level accuracy. So this basically predicts uh, built before methodology. So this is basically built to predict build before. Before the fabrication is done, this is to predict any errors if there are any other errors in the circuitry. So in this spice simulation, there were different breakthroughs done at different times. So initially there were BSIM4, then PSP, then we had different models. So these are all models I'm talking about, different models that were developed at different eras. FinFET, then we moved to gallium arsenide FET, and recently, if not so recently, in 2000s, there were fast numerical solvers that were developed to solve the problem of slowness in spice simulators. And sparse matrix techniques also were used. So in our BTech, we were taught about Newton-Raphson. So we used to think what the use of this would be in our industry. So this is one such area where this mathematical convergence techniques are used. Newton-Raphson is one such technique which basically improves the efficiency of spice simulators. You can go and read about it. Next, coming to, like I mentioned, the complexity kept on increasing as the time progressed. So this is basically what Moore's law says. So what it says is every 2 years, the transistors in a chip would double. So every 2 years, this is doubling. So now the chip, the transistor size, the wafer size have gone to a level of nanometers. 4 nanometer, 2 nanometer chips are being developed. So due to this, EDA tools would have to be also at par with this technology. So this is a very niche area wherein you cannot relax. You have to be on your toes, and you have to be at the same pace at which the design industry is going. The companies like Qualcomm's and MediaTek's are going. So next, coming to key categories of EDA tools. So this is the different phases of a design process which a company normally follows. So there's a front end wherein the intent of the design is captured using HDLs. So HDL is basically the example would be Verilog and System Verilog or VHDL. Next is at this level itself, there is simulation done. So and also for analog side, this schematic capture is also being done. Now let me explain what is RTL. Basically, this HDL, or you can say this RTL step. This is where HDLs are used. It basically describes the data flow between registers in a behavioral manner. So this typically abstract away gates. Now coming to mid-level, the logic synthesis part. So in logic synthesis, this what basically is happening over here is RTL to gate level net listing is being done, which is optimized for speed, area, and power. So at this step itself, uh, the design is optimized for speed, area, and power. So basically PPA, power performance analysis. The input to this is RTL and different constraints and standard cell libraries. Next is backend, which covers the place and route. So what basically is being done over here is floor planning. So we basically plan out the whole IC, or on a broader level the PCB. We basically plan that we need to separate out the RF circuitry from the digital side, because RF circuitry is more what you can say is more prominent for noise. So we need to separate noise from this analog signal. So that part of circuitry is kept separate from other circuitry. So this is so at this step is so at this step the floor planning is done. Also clock tree synthesis and routing. Routing is a very niche area where currently AI is being used. So initially, some time back, around 2000s, the people used to use hand routing to do the circuitry. Next, we moved to some automations wherein algorithmics like A star technologies were also used to route the circuitry. Now we are using AI. So what we are doing over here is we basically capture the intent of a routing engineer using past designs, and we see and we capture what that the routing people do first and what they do next. So basically we have the parameter list of the design, and using that intent we basically come up with a solution, a not so 100% correct solution, but yes, if you can say a routing engineer would do it in a week, after this solution it would come down to a day or two. So the routing engineer would basically start with a unrouted design. Then with the AI solution he would reach to around 90 to 95% of the routing, and then rest 5% would be left for him to do. Next is verification. This is basically functional and timing part. We basically do static timing analysis, power analysis, formal verification. This basically, as I initially mentioned, takes a lot of time. Around 70 to 80% of the time is being done in verification. Next is sign off and manufacturing checks. So this is where DRC is being done. Design rule checks are being checked. Layout versus schematic is being done. So at one window, if you can say, we would have schematic, and another window we would have layout, and we would do cross referencing between the two windows and check whether the layout is correctly capturing the intent of the schematic or not. Also, IR drop and EM analysis are being done at this stage itself. Now coming to why do we need AI in EDA? So this slide basically talks about why do we need AI in EDA domain. As we briefly talked about the tight deadlines. So basically what happens is as the design complexity is increasing, at the same time timelines are also becoming short for a chip to be taped out in a market. So time to market is reducing each and every day. So this basically needs AI to be a chip to come in. So addressing tight deadlines, conflicting PPA goals, and human limitations. So if a person is being doing some kind of a job in 5 to 10 days, AI after using AI, it can be done in a day or two, and this would basically improve the efficiency of the whole design cycle. So the chips would be taped out quicker. AI predicts outcome, automates tasks, and reduces errors through data-driven learning. So basically, it basically tells, so if an error used to happen some down the lane. After using AI, the errors can be checked in initial phases itself. So this is also this is also an important aspect of why do we need AI in EDA. The techniques used currently in this domain are machine learning, deep learning, and reinforcement learning, and also transfer learning. Basically what happens is the AI industry has developed some models, and we basically use those models and fine tune them on our data in EDA domain. Next is what are the key applications of AI in EDA? Design space exploration. So basically, what I mean about what I mean here is, uh, I have an behavioral intent to capture in my design. So what this will do is it will explore n number of basically it will explore n number of dimensions and come up with the best possible design that can be fabricated at the last step. At the last step, placement and routing is another key area for AI and logic synthesis itself. Verification, power optimization, fault predictions, generative designs for custom circuit, autonomous chip design, and there are different companies which are currently doing this. So basically, what we typically do here is we use transformers architecture. You can say encoder decoders to use generative AI as well. So generative AI is another area that has come up recently, which is helping us a lot. So basically, what we do is we take an LLM off the shelf and fine tune it on our data, which is relevant to EDA domain. And after doing that, the designer, which is designing chips, can query his or her database or his or her data sheets in a natural language and come up with the answers without reading the data sheets all through. So this has basically speed up the design cycle. So everything that we do is to uh, leading to a quicker design cycle, a quicker tape out, a quicker time to market. This place and I wanted to basically elaborate on this place and route technology because this is one of the areas that we have worked on in AI. So basically what we have is we give the system an input versus output mapping of the ICs or chips or boards along with how good or bad the placement is, and then train the model. So basically what I am saying is we capture the schematic. I'm talking from analog and mixed signal point of view in this slide. We capture the analog and mixed signal intent in a schematic, and then we move to the backend, which is the layout side, layout part, and we take some of the basically what you can say some of the intent from this step to the layout step. At that step, we do the exhaustive design search. So basically, now when we have come to the PCB level, we kind of do all the permutations and combinations and see what is the best fit from standpoint of routing, from standpoint of power performance analysis, and from standpoint of timing analysis. So we basically have three uh, you, uh, these three key areas we evaluate the model on. And as you all know, this is a very computationally intensive process. AI, so basically this needs huge servers. So what we typically do is We have AWS servers that have large deep GPUs, and we deploy our model over there. So this is a highly computationally intensive process. So yeah, so one of the areas that is currently also growing up is how to minimize the size of the models. So LLMs are huge. So what we are currently working on is fine tune the LLMs and shrink the size of those LLMs to be used on a basic machines. This is tricky, but yes, we are doing that currently, in process of doing that. Another key area that I want to emphasize is another key application of AI is AI driven content creation. So as you all know, when a manufacturer like Nvidia or Texas Instrument or National Instrument or any other company develop a chip, they ship a data sheet along with it. That data sheet is a gold mine. It has lots of data inside it, and designers read through those data sheets manually. So what we can do is we can develop different solutions to capture different information at different stages in the design step. So this is an example which I am giving you, where academia can come in and do a lot of research stuff. So basically, we can leverage different AI techniques to create models which are used further up the ladder. So at the end of it, what would happen is, assume that there is a there is a design engineer sitting in a company called Qualcomm. Currently, he or she is reading datasheet to get answers like what is the operating voltage of this pin? What are the pins in this chip? What is the description of each and every pin? Whether this pin is uh, uh, high or low, whether this pin is active high or active low. All this information he or she would read from the data sheet, and it would take a lot of time. So what we can do is we can enable the design engineer to query in his normal English or any other language he or she wants to, and quickly get an answer to it. So content creation, what I mean by content creation is there are different models that are being used down the, rather up the ladder. IBIS, SPICE, as I briefly mentioned earlier, Verilog, VHDL models. From those data sheets, we can quickly create those initial models for design engineer to quickly ramp up with them. So datasheets is one such gold mine which we can exploit. Next is VLSI development cycle. So basically, typically, what I'm trying to say is, after AI is enabled in the EDA, each and every step in the design cycle would have something or other information to be taken out from those AI models. So this is how the new world of VLSI would look like with AI in place. It will understand all the phases of the design cycle, like design exploration. Basically, here companies are working on using transformers, encoder, decoders to automatically find list of some good optimized designs for given specification in natural language. So the design engineer would query in a natural language, and just like you people currently, if there are students also in this, or faculty also currently uses chat gpt a lot. They query in the normal language and get the answers. So so this same technology can be used at the side of EDA, or at the side of product companies like Qualcomm and MediaTek. So essentially, what it would do is it would speed up all the later stages. So if I have the optimized design at the first step itself, there won't be any need for optimization. I can straight away go to verification. DRC is another such area which is heavily using AI because it has lots of data. Data is king in this era of AI. So this basically typically explains the process of developing an AI model to predict circuit parameters. So once we have the Spice netlist, uh, this passes through the simulator and all the way we have data pre-processing. At this step, we define the input variables and output variables and normalize. So normalization is an important step in AI, in machine learning. Without normalizations, they would be either overfitting or underfitting. So this step is key when we talk about AI in EDA. Then we split the data into train and test part, and typically we use supervised learning. So EDA is more of a supervised learning and semi-supervised learning. So this phase is basically dealing with supervised learning. Once so at this step, we are training the AI model to predict the circuit parameters. After evaluating the performance of AI model, we decide whether we have reached the desired accuracy or not. Otherwise, we basically fine tune the hyperparameters. So hyperparameters basically, what I mean by hyperparameter at this step is required PPA factor. What are the different uh, values we require for different parameters of power performance analysis? So essentially what we are trying to do here is predict circuit parameters using AI. Semiconductor manufacturing is another such area which can use AI heavily because it is highly data intensive step in the whole design cycle. So this slide talks about the scope of AI in semiconductor manufacturing stage as well. We being part of the AI industry don't have much insight into this manufacturing phase, but yeah, manufacturing has a lot of data that can be used for training models and develop new software for automating some of the manufacturing processes. So at each and every step, you would see there is data. At fabrication step, there is data to ensure defect-free device, transistor level fabrication. At wafer test level, there is pre-assembly data to drive specification compliance. Next is final testing. After this very wafer testing and fabrication, there is a final testing done, which basically has post-assembly data to validate the product settings. Then is assembly level inspection. Basically, after every check is being done, we basically the manufacturing companies do this final assembly inspection, where there is final data analysis to capture defects at the last step before they ship out the chips to the market. Then is system testing. Here also there is data, and yes, so there's a lot of other miscellaneous data as well to drive equipment and support systems. Coming to key industries for AI in EDA. So these are the various industries that AI industry deals with when it comes to AI enabled chips. So this we have more or less talked about this semiconductor and electronic manufacturing. So benefits are AI-enabled DDA accelerates chip design, verification, and all the other steps in the design cycle. Example companies which are currently dealing with, which are basically in using these tools. The hardware companies which are using these tools are Intel, Nvidia, AMD, TSMC. One such area for EDA to go into after this AI boom is automotive. The benefit is we have a recent shift towards autonomous vehicles, the ADAS and the EVs. All these require sophisticated, reliable chips which have AI incorporated in them. Example companies are Tesla, Qualcomm, and XP. Healthcare and biotech is another growing area which uses lots of AI enabled chips, and EDA is basically capturing those companies as well. So this is a boom area. This is so the recent times are basically boom time for ED industry with AI in picture. Benefits are we have advanced medical devices and imaging systems which need AI powered custom designed chips. Example companies are Siemens Healthcare. They are heavily investing in this technology, GE Healthcare, and Medtronics. IoT is another such area which I think all of you must be knowing about. It requires very ultra low power chips uh, designed for sensing, connectivity, and example companies are ST Micro, ARM, Espressive Systems. So this slide basically talks about increasing role of AI in semiconductor market. So as you can see in 2025, last year itself, the AI semiconductor market was $65 billion, which is kind of huge. And this trend is going upwards. And by 2034, the estimates are that this pie chart would grow to around $230 billion. So this is and this essentially means more jobs. So this is one such area which academia can come in and basically help the students to get a lot of jobs and high paying jobs, not those jobs of TCS or Infosys. These jobs are typically niche area jobs and high paying jobs. So this is one area where academia can give a lot of research opportunities. Academia and industry itself can come in, have a collaboration uh, to basically open the gates of this industry, open the gates of AI and EDA industry for new software engineers. So yeah, this is what I was briefly talking about industry academia collaboration. So there are a lot of research opportunities in AI driven physical design and hybrid ML techniques. So from standpoint, there are a lot of research opportunities. There are a lot of internship opportunities for academia students, for college students that are basically typically are those are doing computer science or electronics. So this area is basically a mix of both electronics plus computers. Academia can encourage basically combining different so basically the so in academia we should encourage more multidisciplinary courses, and I am aware of many such courses in NCU. So NCU is one of the leading institutions that is bringing about this change of having multidisciplinary course between CS, IT, CS, EC, and other streams. Next is what are the challenges and open problems. in AI when we are using AI in EDA domain. There is a lot of problem of data availability. Every product company like Apple's or Samsung or Qualcomm's that is building chips, each of these companies think that they have a secret sauce which they are reluctant to share with the industry. So this also brings, so this is where the data availability issues comes in. So, and also we have an opportunity. What we can do over here is whatever limited data we have, we can use different augmentation techniques. So the people that are the people that are currently doing MTechs and BTechs can come up with solutions to augment the data that we already have and basically increase the amount of training data that we want to use in machine learning models. Training of AI models is highly complex and computationally intensive and has some scalability issues because each and every design is new. Whatever training we do has some kind of limitation. So after every few years, we need to train those models again. So we have some scalability issues over here. And also the black box nature of AI models and integration challenge. There are a lot of integration challenges as well. So when we deploy or when we train the models on our AWS servers, we need to first install a lot of packages of Python, of PyTorch. They have a lot of dependency issues. So this is what I'm talking about. The black and also the black box nature of AI. So what I mean is a company. There's a company called Ultralytics that has developed the AI models to train the images on. So uh, those companies have though they are working in a black box environment and are not basically giving every parameter to the ML engineer to play with. So yeah, these are also all the challenges that we have to deal with. Next is future trends in AI driven EDA. So what I foresee is autonomous chip design. So it would be in some time uh, an AI powered end-to-end automation would be there, wherein uh, AI would do design exploration itself. It would then do some kind of optimization and then move on to verification. So design engineers would heavily be dependent on this technology moving forward. And with the advent of these generative AI tools as well, this is becoming a reality sooner than later. And yes, what I also foresee is integration of AI EDA advancement into academic teaching as well. So there would be a lot of AI enabled EDA tools that industry would be giving to academia as part of CSR activities. So, as part of this FDP program or as part of this whole journey, we should encourage research and collaboration and focus academic research on impactful short term and long term goals. We should promote collaboration through industry funded labs, joint PhD program, and internship. So, there are a lot of internship opportunities in the industry. Uh, and lot of collaboration opportunities as well between academia and industry. So finally, yeah, the last slide which says that AI is redefining EDA and VLSI design with transformative potential. So this is what we discussed. The potential is huge. As we talked about design engineers being using their natural languages to query the data sheets, to query their databases of those designs. The potential is huge when we talk about AI in EDA domain. And yes, academia plays a vital role in driving this change. They also play a vital role in preparing the engineers for the industry. As part of this FDP, the the teachers they do, and they also must also encourage. They currently do as well, but they should also encourage more curiosity and optimism for future of AI. Not in only in EDA, but every other domain that we can think of. So this will basically increase the opportunities for students to get jobs in a lot of other companies which are currently working in AI. And yes, uh, more or less every AI, every company is currently investing heavily in this domain. So that's it from my side.
So we now move on to the question and answer session.
Thank you so much, Shubham, from the side of all the organizers and participants. So the Q&A can be taken up, and the chat box is open for the questions. So
Thanks.
shall we
Thanks a
take some
lot.
questions, Shubham?
Yeah. Sure. Why not?
So some
Thank you,
participant,
sir.
yeah, is asking that in Spice you had discussed to, focus on something specifically. Something was highlighted in the midway session. She is asking.
Let me check. So basically, what I had spoken about spices. Uh, Let me go to that slide. So basically, initially I mentioned the brief of what spice is. So what exactly is the question? What spice is, or uh, what? I didn't get it. So basically, if I recap, what I said was SPICE stands for SPICE stands for simulation program with IC emphasis. It basically deals with mathematical simulations of circuits. So basically, what we do over here is in a behavioral language, if I say KCL KVL is being carried out on the whole circuitry. Uh, the device level accuracy is being matched, and this basically develops on the strategy of predict before build methodology. So this is what I told. So any questions over here?
I think that's what the question was. So,
Okay.
one of the participant is asking how can AI-based EDA tools stay robust and trustworthy uh, when the
Okay.
future semiconductor designs differ significantly from the data they were trained on?
Got it. So this is a very good question, and I briefly touched upon this topic in our dialogue in our presentation. So I talked about data augmentation. So the data augmentation technique should be such that the model that we have developed today should be capable of dealing with technologies, dealing with designs 5 years down the line, if not 10 years. Every 5 years is good enough if we have to train the model again, or every 3 years at minimum. Uh, the data augmentation techniques, what I mean by that is, let's say I have a leaf and I want to capture what disease it is being suffering from, and I have 100 different images of leaves, of the infected leaves. So from those 100, how can I move on to how can I augment the data to make the data set to 1,000 images, capturing other diseases as well. So I think that answered. I think I was able to answer that question as well. Is
Yes,
yeah,
definitely. So we will take one more question, which says, what kind of research opportunities are there in physical design related to the complex circuits?
uh, from physical design standpoint, yeah, so there are a lot of areas, the lot of emphasis being done on the physical design stage itself, from Verilog to system Verilog. So basically, uh, not from the Verilog language itself, but from the standpoint of compiling that Verilog language to the net listing part. So we can make those engines more robust and more what you can say, we can develop those engines in a such a way that the final net list that we have come up with is has gone into every direction, every dimension, and has finally come up with a solution which is more optimized than what we used to have earlier. So there are a lot of research areas from compiler standpoint, not from language standpoint, not from language standpoint. Yeah. What I so let me open the chat. I think this is uh, I think what is Sir in Spice, you asked us to read something. Okay. Some material to refer was asked by the speaker. Just wanted to know that. Okay, got it. So I will share that material after the presentation. I got it. I got the point. I'll share you. I'll share it. Got it. Anything else?
These were the questions, and uh, some more are.
Thank you, sir.
Yeah, but
I
I
think
mean, we can take one or two more then.
uh,
I think it was discussed. So, one question is like, which skills should researchers or students focus on to effectively work with AI-driven EDA tools? So,
got it. So basically, the skills or technology that you people need to work on is electronics with a computer science knowledge. So you should know, you should be a good programmer, you should be a good problem solver, and at the same time, go and read uh, courses like matrices, determinants. So everything that we do in AI is related to mathematics. So you need to have a strong mathematics foundation for AI to to use AI in your future companies. So yeah, computer science, electronics, mathematics. Uh, I would say do not fear from basically do not have a fear in mind of mathematics. Initially, you can start with, so there are a lot of packages in Python that you can initially start with, and then once you have the grasp of what the what the broader picture is, then you can delve into details of each and every phase, uh, and read different. There are different courses online, different Stanford courses, different NPTEL is one such website where IIT Delhi and different IIT institutes have given lectures online free of cost. You can go and read those courses.
yeah, I think that
Thank
covers.
you, Shubham. It
Yeah.
was a wonderful session. I'm Dr. Pooja here.
Yeah, hello ma'am. Good evening.
Good evening. How are you?
I'm fine. What about you?
I am also doing very good. It was a wonderful session, and thank you being part of this FDP, being an NCU alumnus, and now motivating other academy and the research is a proud moment for the NCU.
All my pleasure. All my pleasure. No problem at all.
Yeah, and it is all you always accept our request. That is a wonderful thing. Thanks
It is
once
the
again
least.
to be part
It
of
is the
this
least.
FDP.
Yeah, it is the least that I can do for my alma mater.
Yeah, great, great. So, Dr. Anu, we are having any further questions?
No, no, I think he has covered all the questions. And Shivam, once again, we are really thankful and we are really proud of, alumnus like you who've been not just doing really well, but, supporting us back there and supporting
Thank you.
the
Thank you.
entire India Semiconductor mission. So
Thank
we
you.
also would like to acknowledge the support of some of the senior professors and consultants who have been constantly joining us. So I would really like to mention that Professor Ramachandra, Professor V.V. Rao, and Professor Swaran Ahuja. So they are very senior professors. They have been joining us regularly in every session. So that really motivates us. And thank you to all the audience. So I think we can take it forward with the next session, and the next speaker is also with us. So we will just give the presenter rights to Professor V.V. Rao.
So before we proceed further, we kindly request all the participants to fill out the feedback form for the fifth technical session that has been shared in the chat box.
The feedback link has been shared in the chat box. Your feedback helps us continuously improve the quality of this FDP.
Good evening, sir. Can we start?
Okay. Uh, okay. So I am visible and audible.
Yes, sir. You.
Okay. And I said just now two more links for animation through the WhatsApp. Whenever if you have that is independent links from the net directly. So whenever I say you can just run it so that it will be more easy for them to follow up. Okay, because I'm going to cover two pumps, major pumps which are required for semiconductor manufacturing. So anyway, shall I start or any other? I think I don't know, no other introduction is required. So I will have to
No,
do
sir.
the introduction
Yeah,
of the topic. Okay. Good,
yeah.
good.
So we will introduce you. So
No, no,
perhaps,
no, that's done. Oh, some
sir, it's,
newcomers.
we need to formally introduce. So perhaps some of the participants. So we will request few minutes so that we can
Okay.
start.
And
Okay.
they also
Yeah.
require some rest, I think.
Yeah. Yeah. Yes, sir. So Krishika and Shivam, just quickly we can introduce her.
Sure, ma'am. We now proceed to welcome our second speaker of the day, Professor V.V. Rao, a distinguished expert in vacuum, cryogenic, and semiconductor technologies.
Professor Rao obtained his PhD in physics from the Indian Institute of Technology, Madras, served at IIT Kharagpur for 40 years, retiring as professor from the Cryogenic Engineering Center, and has recently joined as University Research Advisor at Sri Venkateswar University, Tirupati, after completing his tenure as visiting professor at IIT Tirupati. Professor Rao's research spans vacuum technology, semiconductor engineering, quantum computing, cryogenic engineering, superconductivity, and advanced materials, and he has received advanced training in Germany and France in vacuum and cryogenic technologies.
Cryogenics Council, senior member of IEEE, life member of the Indian Vacuum Society, has published over 110 research papers, guided multiple PhD and postgraduate theses, authored a book on vacuum science and technology, delivered an NPTEL course, and organized 45 short term courses.
In today's session, Professor Rao will be sharing his insights in continuity with the session he conducted yesterday, further strengthening the concepts discussed earlier.
Sir will be elaborating on these ideas with more advanced concepts and practical insights drawn from his vast academic research and industry experience. The chat box will remain open and the Q&A session will be taken at the end. We now invite Professor V.V. Rao to kindly begin the session.
Oh, thank you very much. Uh, it was my pleasure yesterday to interact with all the participants for various aspects of vacuum technology relevant to the manufacturing of semiconducting chips, where we mentioned different levels of vacuum are required for different applications, whether it is a metallization or a doping or initial cleaning or wafer level or lithography or some etching or ion beam etching or many other processes are there to basically make PN junctions or PNP transistors or CMOSs, connect them with resistors, capacitors, and such assemblies millions in the form of small dies. And after testing everything in the wafer level and various other levels, nearly 150 layers, we need to take them into another place for packaging. So that is called front end and back end processes we have explained. And today, just now, he has explained that EDM tools, which are actually fab design. So they will actually do this, whatever they are physically going to do in the chip after switching on the vacuum ambience and various power supplies, various electron beams, ion beams, ready for the soldiers to make the chips on a nano scale and several such micro dots and with different dice, and each die goes into one of your cell phone. So when this is all going on, there is a continuous interplay between fab design and the testing and the reliability analysis, VLSI design, and at the same time materials controls. Back of all this is the clean atmosphere. Otherwise, whatever you wanted to do, it is something like making a beautiful hard work with a lot of spices and beautiful rice, etc., and make a palau. At the end, something happened and some cobweb or something fell onto that. So if the vacuum is not good, nothing works finally. Okay, so that's how we have confirmed yesterday various aspects of it. But because of lack of time, I've only mentioned production, measurement, system design, troubleshooting equipment. But today, I wanted to also give you a flavor of that production of vacuum, because it is not fair on my part to say vacuum technology unless we say something about how to produce vacuum. And measurement, even if I don't explain, it's okay. Because if I tell the units and it's basically instruments, you are not going to make instruments and they will not foul. But most of the time you are busy in handling the pumps, connecting pipes. And if something wrong goes wrong, you will have to troubleshoot. So the system design already others are taking, and application is basically thin film as well as semiconductor manufacturing in the form of a chip and packaged chip. And measurement of vacuum technology, I don't intend to cover because it is very simple things, and on some other day we can cover. But the production of the vacuum and troubleshooting of the vacuum often will be the main tasks of an engineers, multiple people who are involved in this high-tech manufacturing. There are, I say, almost equal number of engineers as the designers. In fact, as time passes, when the AI comes into picture, more of the design and engineers will be replaced, more of the simulation engineers will be replaced by machines. But the hardware engineers cannot be easily replaced because it's tough because unless you properly take care of every aspect in a very high-tech manner, things will not listen. Though sometimes robots may replace, but these require within the vacuum. So you need a micro robot. That's a big research. It will take a long time. But AI is coming up in a big way. So that way, the design things and intelligence has become artificial, but the skill cannot become artificial. So we'll have to understand there will be a lot of scope as time passes after 5 years, after 10 years. The mechanical, electrical, electronic aspects of it are new materials aspect. So in all this processing of these things in the form of materials or wafer level or chip level or packaging level, the production of vacuum is important. So we have confirmed. I'm trying to give you a same continuity of thought. But today I'll only cover some most important pumps which are required for semiconductor manufacturing. That is from the atmosphere right up to 10 power minus 9 tar, we have to go. Atmosphere is 760 tar. As yesterday I already told you, you must be remembering 760 tar is same as 1000 millibar. Okay, so even in millibar, if you say you don't make a massive mistake, it is only the same order. So from 1000 millibar to 10 to the power of minus 9 millibar, you can go with just two pumps. One is a rotary vane pump, other is a turbomolecular pump. There are finer variations of this rotary pump in terms of other pumps, but right now we need not talk everything in the world today. So if you know the starting vacuum pump, which is called roughing vacuum pump, and we also know the high vacuum pump, which will finally take it to the necessary ambience before the IC chip manufacturing process starts physically. So just for a flavor of vacuum, yesterday also I told you as you go up, different levels of layers, we have different vacuum naturally available. And some of the applications and ranges of applications I have given in the left side, where I have mentioned, if you go to 10 power minus 9 tar, is absolutely required for the satellites which are responsible for you to listen what I'm talking, which are responsible for all the cell phones. So right side I have given various pumps, and broadly I have classified into two types. One is primary, that's called, sometimes people call backing or roughing pumps. They will take from atmosphere to a respectable vacuum called 10 to the power of minus 2 millibar or minus 3 millibar, beyond which the mechanical pumps cannot work. And they require some hypermechanical pumps like turbomolecular pumps. They don't pump gases, they pump molecules, whereas the primary pumps pump the gas. That means gas is removed, you get vacuum. That is primary vacuum. So 99.9% of the air is removed in the gas manner. Whereas afterwards, these become molecules. Yesterday, those who have heard, they know very well, as you go to 10 power minus 3 or minus 4 tar, we end up in an ambience where the mean free path is very long. The molecules will behave independently. Nobody will drag anybody. It is like entire Indian country, instead of 130 crore people, only 13 people are there. Then how much area you will get? It is somewhat like that in ultra high vacuum. The entire chamber, only few molecules will be there compared to the atmosphere. So that time molecules will not hit each other. Most of the time they hit substrates or they hit the walls or components. So when you produce some extra molecules in the form of silicon vapors or metallization, they will dominantly go in the straight line path and get deposited, which can be controlled very nicely in that atomic scale and nano scale, so that whatever fab designs you are making with L, C, R, etc., and try to do that system analysis, the Kirchhoff's laws. That's what just now he told. All that voltage laws, Kirchhoff's laws, and all, they are all embedded into the software. But that circuit has to be physically here. So this circuit, they will test it. Here, even physically also you should test it. So all these things within the vacuum, how are you going to do, how the system look like? And finally, if the vacuum is not coming, how are you going to troubleshoot? So that's how we talk about it. But much more details, system design, effect of piping conductances, calculations, we require another 2 3 classes that we will see some other time. Otherwise, you can find very good books, or you can go through my what you call web, my internet lectures are there, and you can easily go, because I have given a SWAYAM NPTEL program for vacuum technology for process applications, where I have covered production, measurement, system design, troubleshooting in a 60 lectures of 40 minutes duration. So you can enjoy that. Okay. So basically, we have primary pumps and secondary pumps, and which are taking your ambience of that chamber where all these semiconducting materials and various manipulators, as scanning electron microscope, instruments, analytical instruments, and shutters, heaters, all of them are staying in that chamber. That's called vacuum chamber, and it is connected by walls by pumps. And if it is a very wide wall, that's called gate wall, like a big, what you call, that we'll see when the walls come. If you're a very rich man, when you enter into your palace, people don't open the gate like this. People open gate like this horizontally. The car will go without any problem. They are called gate walls, gates. Whereas if you try to do like this and slightly like this and all small things, they are throttle walls, they are control walls, etc. So they're depending on the conductance for the flow of molecules from the chamber to the pump, you require different valves. Of course, your cost has to be there. In a typical environment of laboratory, you may not be able to handle such high costly valves or high costly chambers or big pumps. But in the actual fabrication, in the actual that is that's like it's like a carpentry house type thing. So when you enter into that, it's a huge lot of big pumps chambers. But you can do all that in a small scale in a research laboratory. This is how in states and various countries people do advanced research in semiconductor manufacturing, and then they send it to Taiwan and other places where manpower is easily available and skilled trained manpower is available, which we can also do it here. So things are changing globally. So there is going to be a lot of importance in clean and green, energy efficient, highly precise manufacturing point of view, electromechanical and pneumatic varieties of devices. So we'll have to understand all that precision engineering. Parallelly, the design and high-tech software programming, which will manipulate the equivalent of manufacturing in a mental scale and that artificial intelligence scale. And finally, it comes to the intelligence to make the things in the actual front floor. Okay, let us see. Next slide, please. So don't bother. I will be doing bits of information. So whenever I tell that, that's that. Whenever I tell something else, that is this. But all of them are requirements. So in the limited time, I'll have to cover some aspects of vacuum. So right now, what I'm going to start now is a rotary vane pump, which is the number one pump. And they have nicely named it as a rotary club. So rotary vane pump, and it is basically rotating. There are vanes which will sweep, and in the rotate, it is like a typical turbo compressor type. There is nothing. So you can straight away watch this. Oh, he has helped. Fine. He or she has helped us. Now you can see. My job is simple, but I will make it little complicated later. First, you just watch this for a few minutes. There is a stator. There is a rotor which rotates. And in the rotor, there is a diametrical slot. And in that slot, there are two plates, and these two plates are separated by springs. Because of spring action and centrifugal action, they will touch the inner lining of the outer box, that is called stator. Mechanical rotor. The rotor is pierced by a diametrical slot, and it will not become two pieces. It is pierced over a certain length. It is like a cylinder, as 90% of it is pierced through a slot, and through that two vanes, rectangular pieces are inserted with spring connections, so that the vanes will try to go in the centrifugal action, touching the inner lining of the thing. So that's how it is shown. If you want, you can show animation once more. If it is
Rishika,
possible.
just yeah.
Yeah.
Animation one, can you please
We,
open again?
yeah. We have enough time, don't worry. And whenever you get doubt, you can ask, because it is down to earth, but 10 power minus 9 tar. So it is a high-tech affair. So you can run it on slow speed also, or you can stop like that. So basically there is a suction line, there is an exhaust port. The red color arrow is exhaust to the atmosphere. I told you yesterday, the exhaust is connected to atmosphere. So the topmost box is like a mechanical engineers know very well. It's like a crankcase. Okay. And now you can come to my slides. I'm sorry, I'm trying to make you hurry. Nothing, no hurry. Slowly do it. Okay. Now, you can just read for your sake, because an engineer can easily follow the things. Just half a minute, you read what is there in the left and what is there in the right, 1 minute. I will explain from the scratch again. Okay, just read once. It is basically right side. I have shown a figure having a rotor eccentrically situated in a stator, and one exhaust valve, one inlet port, and inlet filter. These are all the standard words that we see in the day-to-day world. Even tea making machine also contains similar things. Okay, even the typical squeezer of this juice, typical juice that we are taking, all that double roller type of things. These are all rotating machines. It is a very simple affair. So, but I want you to say, read once left side. You may not follow or you may partially follow. That is okay, but still read because the words you have to understand. If it is possible, you can even download all these things on your cell phone and you can start reading in your cell phone also. If there is a procedure like that, you can get it instantly. But otherwise, you please read the things. Show the slide. Slide is not visible to me, but I hope for yeah. So just read it. You also read the right side. There are 11 parts uh, shown in the figure as well as the caption. Just try to link it one to one correspondence. I will talk about it anyway. Okay, assuming you have done some homework now by now, uh, just some of you might have followed easily because similar structures are available in rotating machines in mechanical engineering and electrical engineering. It's not a difficult task at all. But if you want to understand any high-tech vacuum pump, first you should identify the individual components and try to figure it out what is where and what is its duty and why it is there. If you try to understand, then assemble all of them and then try to understand again little bit. It is like an electrically first inductor resistor, but when you couple, you will have a circuit. When you do some active element like transistor, you will have another intelligence to that. Similar way in the mechanical thing. Now, if you carefully observe, something is rotating. Okay, what is that called? It is a cylinder. I have shown a cross section, but actually it is a three-dimensional thing. It is a cylinder. Okay, and in the center there is a diametrical slot cut. Focus only on rotor. Don't worry about all other things. That rotor, it contains one spring type of thing, and it contains two vanes type of thing. Vanes are nothing but a rectangular plates like this. When they go into this in the long way, because this is cylinder with a slot, in this slot it will go. Another thing will come from that side also, one slot. These two things are supported by the springs so that they will always try to go out. And this mechanism is called rotor mechanism with spring-loaded vanes. Now this fellow is eccentrically situated in another circular fellow which is called stator. That's also cylinder. That's a hollow cylinder. This is a solid cylinder. Okay. This hollow cylinder is pierced with two holes in the periphery by two ports, which is an inlet pipe, other is exhaust pipe. Okay. Now the exhaust pipe is terminated with a flap wall. It is like if you take a tongue cleaner and try to do like this, it will try to close, but whenever there is high pressure, it will open like that. So whenever you go to some mela, they try to rotate something, and if you are lucky, if your number comes there, you will get money, and it keeps on going in various sectors, and whenever it goes up and down, up and down. So that flap wall is exactly like that reed that tries to open and close, open and close. When it will open, if the inside this side pressure is more than the other side. Okay, so try to understand each piece of equipment just as a machine equipment. Don't worry about vacuum pump, semiconductor manufacturing at this stage now. Within 5 minutes, we'll come out of this boring things. But till that time, you try to understand as they are identified individual parts, basically. Okay, that's the best way to understand any machine in a mechanical engineering. Otherwise, you will get tired when you go look at the car having so many things. But each element, if you understand individually and then couple it, it is very easy for you to. If you are a mechanical engineer, it's all the more easy. Now, entire stator and rotor assembly is submerged in oil. That crankcase is also called oil tank. So there is an oil tank, there is a crankcase, there is a stator, there is a rotor, there are two vanes, springs, inlet, exhaust port. Exhaust port is connected to exhaust valve, and actual semiconductor manufacturing chamber. Okay. So which is at atmospheric pressure. Everything is at atmospheric pressure to start with. There is no vacuum at that time. Okay. Everybody, when we were born, we don't know even ABC. We'll have to start learning. Same thing in the beginning, the chamber is at atmospheric pressure. There is no vacuum, there is no semiconductor, there is no electronics, no software, nothing. Now, this pump, what it will do, it will suck some part of the gas because of the volume increase, because of eccentricity. There is a joke also in the rotary pump. Sometimes eccentric people, they are responsible for all the discoveries. Normal intelligent people can understand things better, can reproduce things better, can do things faster, but they cannot invent. It is only the crazy ideas, crazy people which are eccentric, they can easily. And same thing here in this rotary vane pump, the rotor is eccentrically situated in a stator, so that it is almost touching. If the rotor is here, stator is here, it's almost touching to the top. See, if this is my rotor and stator is there, it is almost touching. You can see there also. So there is a bottom, there is a lot of gap. But these vanes, what they are trying to do, they are touching the inner lining. So there are three touch points. One is the rotor is touching the stator, that's called top seal. And the two pieces of vanes are touching because of centrifugal force at two other points. So in a rotary framework, if there are three touch points, you will get three volumes. Is it not? If it is concentric, you will get only two volumes because the third point is not touching. It is like a stator and rotor, and two vanes are there. Even though vanes are there, top half and bottom half, only two volumes. Two volumes cannot do compressor action. Three volumes are required. Okay, that is the heart of rotary vane pump. So this is the called construction of a typical rotary pump. Already action, you must be getting some idea by the animation. Okay, so now go back to the still picture. No, that my slide. Good, you are able to do it. Now zoom that figure little bigger. try to zoom that. This was a cross-sectional view of a typical rotary vane pump, which is there in almost every vacuum pumping system. So if you understand rotary vane pump, it is heavily manufactured in India as well as in abroad, depending on the type of the material, quality of that, and finishing of that, cost changes. And very high quality rotary pumps can produce 10 to the power of minus 3 tar, and normal pumps can produce, Indian pumps can produce minus 2 tar. But these two are good enough to remove 99.99%, because 1000 millibar, whether you go to not 1 millibar or not 1 millibar, already 99.99% has been removed. The cost of these pumps are only 30,000, because it contains some stainless steel cylinders, rotors, and oil, lubricating oil, and crankcase, one exhaust valve, an inlet valve. And when the air is being sucked, if there is some dust or anything there in the chamber, the dust should not come into this rotating machinery. Then instead of rotary pump, it becomes a grinder, because the dust enters. It is only supposed to suck the pumps, sweep the air, suck the air, sweep the air, compress the air, make the exhaust valve open, throw it out. These are all the four sections. Okay. So how do we do it? There should be some filter in the inlet. So now if you come to that, one is the inlet. So you can see the inlet pipe. Then two is the inlet port. Okay. The place where the molecules are coming is called port, and the channel is called tube. It is a simple structure. Then the touching point, apparently touching, it's not touching. There is a micron gap. And that micron gap is sealed by an oil film, because entire body is submerged in oil, and under vacuum there will be some flow of oils through those various mechanically connected joints, and they will enter and quickly lubricate the entire inner structure. And when it is tried to lubricate that, the veins which they are moving, even though they are scratching, it will, because of the lubrication aspect, the wear will not be there. And the veins are also nicely tapered in a semicircular way at the edge, so that the touch points are very smooth and they will not be scratching much. So all these precautions in the machining and all is a typical job. I'm trying to explain unnecessarily more, but those who are non-mechanical engineers, sometime or other, if you learn this mechanical precision engineering, you can enjoy life, I'm telling you. So a rotary machine is a very interesting thing. Same machines with the time, if you are having turbines, then turbo compressors are there. Everything is a rotary machine. Whole world is rotating only. Okay, so you'll have to understand this rotary motion. Then, of course, linear motion, all these things are there in our school studies, and reciprocating machines, etc. But this is a rotary machine. Okay. So third is that. Four is the vanes. And five is the oil. What is the role of oil here? Oil will act like a lubricant. Oil will also act like a sealant, because unavoidable some small leaks may be there in the body of the stator, so air will rush in. So if there is an oil on top of that, then air has to come through the oil and go into that inner space of the vacuum pump. So that way it is difficult. So oil will act like a barrier for the atmosphere air not to enter into the vacuum pump. If it enters into vacuum pump, how vacuum pump will create vacuum in the chamber? Vacuum pump itself, its vacuum is spoiled. First of all, vacuum pump has to be evacuated. Then when it is connected to the chamber, the vacuum pump volume plus that volume is made to increase. That's called compression expansion. And when it is increasing, PV is equal to nRT. Number of molecules have not changed, but effective volume has become, instead of 100 liters, 100 plus 100.01 liter. Because that not one is coming in the right side, that crescent like volume, which is increasing volume. Okay. This volume, when it is increasing, that is between the rotor and stator and that vane and the top. So that isolated volume, a moon-like structure, is coming slowly increasing volume. On the left side, there is a decreasing volume. And in between the vanes, there is a sweeping volume. So you increase the total volume of the chamber plus this volume, and thereby pressure is falling down. because instead of 1000 millibar, it has become 999.99 millibar. Okay. Because that much V1 by V2 is equal to P1 by P2. Okay. V1 by V2 is equal to P2 by P1. P1 V1 is equal to P2 V2. As simple as that for a given number of n molecules. So this is how suction takes place. Sometimes they call induction. After some time, that this vein will come there because it is rotating. Then what will happen? It has sucked by increasing the volume, but this vein came, then that particular volume is called trapped volume. This volume contains certain molecules which were there originally in your chamber. So you could remove 1% of that. So it has become 998 bar, millibar. So next stroke 996. Like that, so many strokes are there. If the number of revolutions is n, and if that one sweep volume, just when the next vein comes to that side, just when it is isolating, if that volume is v, and that situation will come twice because this vein comes to that vein comes to this side in one rotation. 2 into that volume multiplied by number of rotations, 2 into V into N is the pumping speed. That is volumetric pumping speed. N has no unit, so it is a volumetric pumping. N is per second unit, N number of rotations per second or per minute, per time unit. So it will be a meter cube per time. So that's called volumetric flow rate. That is the called pumping speed of a pump. Now, I told many things. I hope you understood something. Otherwise, also doesn't matter. Now, when you go through slowly in the book, etc., you can easily understand. But this is the terminology. Next slide, please. Yeah. Now you can see same thing I have shown in 4 stages of that rotor stator assembly. So one vein is just about to close that. So that is the total volume of the air which was belonging to the chamber. It has also occupied to partly here. So you have isolated it. So second stage is isolation. The third stage is compression because volume is decreasing. Right side volume is increasing, left side volume is decreasing. For the same number of molecules, when the volume decreases, pressure increases. When volume increases, pressure decreases. So suction side, we get an increasing volumes, and compression side, you are getting decreasing volume. And when the pressure in the dead volume, which is not coming into the rotary motion framework that is connected in the body of that rotor, that's called dead volume. It is there for top dead center, bottom dead center of a typical IC engine. Same language here also. If that pressure is more than the atmospheric pressure, plus the hydrostatic pressure of that oil in the tank, then what will happen? Valve opens because it is a hinged between, it is a small diaphragm, a rubber diaphragm hinged between a metal plate and the top of this exhaust port. So it pops up, it pops up like this. So whenever pressure is more, it opens. And as soon as it is exhausted, a suction, sucked, isolated, swept, compressed, exhausted. These are the 4 stages. These are explained below. So with this idea, I want you to again read this notes and that figure for 1.5 minutes. Anyway, I hope you got something. Actually, in the class to our BTech boys, we try to open things and try to explain parts, identify, then run the things, design, and it will take 3 to 4 hours even for a pump. But here I have to take half an hour or 20 minutes. That's why it is tough, but it's not difficult. You can easily follow it up. After that, also you read these slides. If there is any doubt, you can always call me. Okay. Assuming that you have understood, this is called rotary vacuum pump. This pump, what is its role? It evacuates the chamber from atmosphere down to 10 to the power of minus 2 torr. What happens at 10 power minus 2 torr? Why can't it keeps on removing the air? You don't require another turbomolecular pump or high vacuum pump. It itself can produce? No. Because there is a finite dead volume. Okay. It's not zero dead volume. So when the pressure is in the chamber is going down to 10 power minus 2 torr, even after collecting, sweeping, isolating, sweeping, and then compressing, the exhaust valve is not open because 10 power minus 2 torr, that much volume has been collected, extra volume, and isolated. That much volume is compressed into this much dead volume. And even under the dead volume, the volume is not zero volume, the pressure is still less than 1000 millibar. It is only 100 millibar. It is collected at 10 power minus 2 torr and huge compression also, but not much. It is only the 100 millibar. Exhaust valve does not open. Why should it open? Now, the other atmosphere is 1000 millibar. In the compressed zone, which is accumulated molecules, which cannot cross the top seal because there is an oil seal. So from the exhaust port to the suction port, it cannot pass. So it is only temporarily staying. As soon as vein crossed, since exhaust valve is not opened, this side still lower pressure is there, they will re-expand back into the chamber. So like this, going up and again coming back. So virtual work, no action is happening. So that is where it stops working, the mechanical device. But it has done its duty of 99.9% removal. But its cost is only 20,000. Now this not 1% removal, we are going to spend 20 lakh rupees. That's also a rotating machine. That's a turbo molecular pump. That's also rotating. Instead of a rotor, it is a turbine rotating. But stator is same. Okay. That is also a cylinder. We'll see that as the next pump. But this is the basis of the rotary pump, which is removing 99.9%. Since it is removing at higher pressures, the work done is more here. That's why the motor rating for the rotor is always higher, half a kilowatt to half HP, 1 HP type of powers, depending on the flow rates or the pumping speeds you want it. All these units, concepts, it's tough for me to explain because it's a limited period, but you get a feel of it. Okay. So whereas turbomolecular pump from 10 power minus 9 to 10 power minus 2 torr, it is compressing. Whereas this rotary pump is compressing from 10 power minus 2 to 1000 millibar. Okay. It's huge compression ratio, namesake, but molecules are not many. So the thrust is not much. So the motor electrical power requirement for the turbomolecular pump is not much. So it's a small pump, but it's a high-tech pump. It costs 20 lakhs. Because your molecules are pumped, turbines are rotating at a high speed of 1 lakh revolution per minute, thanks to the offshoot of turbo machines in the planes, and with magnetic bearings, etc. A mechanical fellow is rotating. We'll come to that later. A typical fan rotates at 1500 RPM with a slip factor of 0.5. Otherwise, typical full speed is 3000 RPM. Okay, 50 heads into that speed. If you have 2 pole motors, you know the typical formula for the speed of a motor. I'm not going into that electrical side. But whenever you are talking about machine theory, you should also tell the power requirements, friction requirements, energy analysis, exergy analysis, and rotating assembly. What is the maximum compression ratio? And is it producing heat? Heat of compression is how much? All that you have to do it. So the oil is doing that role. Oil is acting like a coolant because it's a huge thermal mass, and that entire crankcase has got fins. So it transfers that heat of compression through the oil into the body of the crankcase. Through that veins, fins, that heat is taken out by the natural convection into the room. So one of the role of the oil is coolant. The other role of the oil is sealant, because compression is this side, expansion, there is a top seal. It is not fully touched. If it is fully touched, it is welded, but it's not that. Slightly this. That micron gap is filled. That is called sealant. So same oil is doing sealing duty, same oil is doing cooling duty, same oil is doing the lubricant duty, because the veins are rotating. There is a machine mechanically scratching, but they should not scratch, use. So it is a sort of lubrication. Okay. And finite pumping speed, because at once at ultimate vacuum, the pressure is so low, even after compression, the exhaust valve is not open. So best way is, instead of connecting it to atmosphere, you connect it to the inlet of another rotary pump. So this second rotary pump thinks that there is an ambience of 1 torr. So it will go up to 10 power minus 2. Otherwise, it would go only to 1 torr. Now it will go to 10 power minus 2 torr. So two stages when they are connected in series, the final exhaust is happening. The in between there is no exhaust valve. The exhaust of the first stage is directly connected to the inlet of the second stage. Only there is single exhaust and single inlet for both the pumps together. This is called two-stage pump. So all that you try to read at your leisure and try to understand at your leisure. And next slide, please. So this is how the rotary vane pump is manufactured. Initially, have you understood something? I hope so. But otherwise, it's a mechanical device. If they give me 2 hours time, I can keep on talking, but that's not possible. We have to go to ultra high vacuum. Then we'll have to do some troubleshooting. That's why this much is enough for the present. But there was a problem. Supposing the engineer was tired in the hot summer, and he puts a drop of water in the chamber, and then connected. He was not seeing that small drop, and it produces huge amount of water vapor at 10 power minus 2 torr. And when water vapor is to be removed, instead of air removal, water vapor under compression zone, since it reaches the dew point, okay, so what will happen? It will form a droplet. Instead of gas compression, it's a vapor. There is a difference between vapor and gas. Gas can be only compressed. PV is equal to nRT. But state of the matter has not changed. But vapor is not like that. When you compress the vapor, it becomes liquid. When it becomes a liquid, it follows the gravity law. When it is a gas, it follows the delta P law. Pressure drop, flow will be there. But if it is a liquid, it is a gravity potential. Delta G, delta X. So it is a mgh. Delta H is more important. Whereas for the gas, it is delta P. So all these concepts mechanical engineers know very well, and because fluid mechanics, thermodynamics, heat transfer, these are all interrelated disciplines, basically a thermal engineering. Okay, and machines when you make, you'll have to take care of all this. And when you connect it to an electrical world, finally there will be a motor when you want to do some motion. So you'll have to do that seals, how that shaft is connected from the motor into this vacuum assembly through a shaft seal. That is also very important. So if you take care of all that, even then, if there is a moisture, you get the moisture saturated vapor pressure is crossing the existing pressure, it will liquefy. So it will follow another rule. It will not follow the Boyle's law. It will follow some other law. So you are in trouble. Okay. So at that stage, what you do is, initially when rotary pump was discovered, for 10-15 years in the rainy period, whether it is a semiconductor manufacturing or a TV tube or anything, they stop manufacturing because they are not getting better than 10 torr. Because that is the saturated vapor pressure where under the compression, the water vapor is liquefied. So you are not able to produce, it is going back and forth. So chamber is having that small amount of residual 10 torr pressure of water vapor. One mechanical engineer like you, intelligent fellow, what he did was, he blew some dry air through that and reduced the partial pressure of this fellow, and that means make it bad. It's like medicines, antibiotics. You try to give some bad things, and then they try to increase, and along with that, a lot more anti things will be created, like first year temperature increases. So antibodies will develop much more. Same thing here. If you try to make it more bad, already it is getting 10 tar. If I make it 20 tar, but the extra pressure is because of dry air, now partial pressure content of that water vapor is now less. So even under that exhaust stroke, these floating dry molecules are able to carry these water molecules before coalescing them into a droplet. So that is sort of a mechanism they worked out using Dalton's principle and Clausius-Clapeyron equation, vapor pressure data, etc., etc. They try to make it so that water molecules are confused in the compression stroke, not to coalesce into the form of a drop, but to disperse like a molecules in the otherwise dry nitrogen molecules, which are intentionally thrown into the body of the rotary system. So this problem was solved. You can read it at your leisure later. So just I wanted to explain that. So this problem, if it is solved, then only we could use this rotary pump. This is the story of rotary vane pump. Next slide, please. Now we have got 10 power minus 2 tar, 2 stages, water vapor removal with air blast, all the concepts, rotary concept, rotor, stator, eccentric, oil, lubrication, sealing. This is mechanical engineering. But now we are going molecular engineering. That is somewhat different from mechanical engineering, but it looks like mechanical, but it's not mechanical. It's a molecular. Okay. This is the next pump. What it's doing after getting 10 power minus 2 tar by this less costly pump, but which has taken 99.99%. This fellow comes like a hero, and I will remove this rest, not one, but I am very costly. So this is the called turbomolecular pump. So I want to explain this also for some time. Turbomolecular pump, it's tough to understand because it's a molecular phenomena, but it's not difficult. I think time is running, so I'll have to be a little faster. Otherwise, I'll leave for some other things later. That's okay. But turbomolecular pump is the heart of all the semiconductor manufacturing. Most of the cost of the semiconductor manufacturing goes in these pumps only, and the chambers and the seals. Rest of the materials and all maybe 100 crores. But 500 crores is gone in these vacuum chambers, vacuum flanges, gold gaskets, these copper gaskets, turbomolecular pumps, maintenance, rotary pumps, interconnecting pipes, their design and manipulators, all this mechanical stuff. But this is one-time things. You have to, whereas the other thing is continuously you have to put the wafers, continuously you have to cut them into things and put them, that is consumables. Okay. So both are important. What is turbomolecular pump? Forget about rotary pump now. It has produced. It's a mechanical motion. But in turbo, it is different. It's a turbine. Turbine is nothing but a disc, but instead of a complete disc, it has got blades. That means there is a openings. Okay. It is like a fan. If there are aerofoil, it need not be there in vacuum technology because that aerodynamic thing is only for gases. In molecules, you don't have to make it aerofoil shape because there is no streamlining, there is no streamlines, there is no viscosity concept. No molecule is heating with the other molecule. They are all heating only body of the turbine blades. So whether it is the roughness, even if you make it 0.1 micron, even then it is 10,000 molecules diameter. So it hardly matters. It is everything. Every surface is a rough surface. Okay, because molecular diameter is 3 angstroms. So you cannot make not 1 micron finish. Micron finish itself is mirror finish. Okay, if you go to not one type of thing, you can see your image even on iron because the wavelength of the light that is falling to create image is 4,000 angstroms, that is 0.4 micron. So if you go to not 1 micron, it is much less than the wavelength. You will see the perfect reflections. These are all the optics fundamentals. Okay, but the such type of finishing has to be done when you go to the turbomolecular pumps, when you go to the chambers which are compatible to ultra high vacuum. So here we see some blue colored things which are turbine blades. There are also red colored blades, which are also turbine blades. But these red colored things are bent this way and blue colored things are bent like this. So, okay. And there are series of red color, series of blue color. All the blue colors are commonly connected to a shaft which rotates at 1 lakh RPM. Imagine mechanical fellow is rotating at 1 lakh RPM. 1 lakh earlier in 35, 50, 60 years back, we used to think 100 kilohertz is the electron motion. But here, 1 lakh, a fan is rotating 1 lakh times per second, per minute. It's not easy task. The bearings, the balancing, if there is excess weight in one side, if it touches the second set of blades, which are stator, the red looking blades are called stator blades. The blue looking blades, both are turbines only, but one is not rotating. They are connected to the body through the slotted structure, and they are touched bit like two split rings. They are connected in between the two rotor blades, because you may be wondering how the stator fellow is not rotating, because there is a hole. It's a typical donut type of thing. It just connects, and on the periphery it is supported by the body, and this all the blue colored things are connected together to a common shaft. Anyway, they are counting -1 torr, not much of stress is there, so they are connected to a small bearing, etc. in the bottom. But top there is a -9 torr. Degassing and greasing and all is not allowed. There is a magnetic bearing. All that precautions have to be taken care. When you do that, a set of rotors rotating at high speed, and in between two rotors, if you are interceding the stators, that combination gives you like a turbojet engines. Whenever you go to the airport, you just see how these engines are looking like that. There are rotors and stators, because velocity energy is converted into pressure energy, and again velocity energy. It is redirecting the flow. So these rotating turbines are giving the velocity, but then immediately the reverse bent, not moving type of turbines, they are stopping this, so the pressure energy picks up. So that way you connect the velocity energy, give the velocity, the sucking is happening, but this sucking is molecules are thing. And these molecules are going to the right side. They are again random velocities. Random velocity is called pressure. Particular velocity is called velocity. That's who has understood. Bernoulli has understood. For us, any velocity is velocity. No. Random velocity is a scalar, because it moves like this and it moves like this after some time. Net velocity is zero. Net displacement is zero. So random velocities are called pressures. That's called P is equal to 1/3 mnc square bar. That is thermal velocity. Okay. So right side there is a velocity, but air is not moving. They are not air velocity. They are molecular velocities. Okay. Now we have to talk about those molecular velocities, because air velocities are all over by the rotary pump. Now there is no more air. All are molecules. We have to catch the molecules by statistical way. If they are moving everywhere, it so happened they come to the pump side also, some fraction of it. So statistically we have to calculate what is the number of molecules coming. At that pressure equivalent, we'll have to think that many liters of gas has come. But actually there is not gas, it is a molecules. But the pump is also molecular pump, because each molecule, when it hits the turbine, it gives the additional momentum to each molecule, and preferentially because of the direction of the turbine, it goes to there. But the next turbine is rotating in the, so it's not rotating, but relatively speaking, it is rotating, but it is actually static. And that is breaking the thing. So what is the role of a stator turbine? It is to convert at each stage the extra imported velocities into random velocities. So the velocity energy is converted into pressure energy. This pressure also is a velocity basically, but this is a thermal velocity, 1/3 mnc square bar type thing velocity. Because here also, even if static air is there, you think it is static. I feel sultry. No, molecules are moving at 300 meters per second here, right here. But we don't feel that, because they are randomly moving. Sometimes this, sometimes micron level. So as a whole, that looks like a static air. Air is static. Molecules are not static. This is the kinetic theory of gases. So this they have taken into advantage. When that molecule hits a turbine, the turbine is also rotating. If that molecular velocity is 300 meters, if the turbine tip velocity is also made to 300 meters, how do we make it? R omega. If speed is changing, even a small turbine, the tip speed will be of the order of the free molecular velocity coming out of the thermal energy, internal energy. From that thermal energy kT, there kT is equal to 3 by 2 kT is 1 by half mv square. You must have read all these things in the kinetic theory in the 11th class. You might have forgotten or you might not have understood in the atomic picture. You please read it again once more. Okay. So these molecules, when they are hitting alternatively, they are sucked, their velocity imparted, and again pressurized, and again velocity. Okay. So this way you get a series of compressions 10 power minus 9 to minus 8, minus 8 to minus 7, minus 7 to minus 6. Like that, there are 9 sets of stator and rotor. And the front surface is called the orifice, which is connected to your semiconductor manufacturing chamber, which was initially connected to the rotary pump to bring it to minus 2 torr. If you don't bring it to minus 2 torr with that rotary pump independently, you can't get this molecular phenomena. You will get high speed turbine will be braked, that 1 lakh revolution will become 100 revolutions because it is an atmospheric gas. We cannot pump atmospheric gas with this turbomolecular pump having some 10 watt, 100 watt motor. Okay, work done is not much, but the quality of compression is very high. 10 power minus 9 to minus 2 it comes. So in every stage, there is a compression ratio of 5. You cannot create one stroke 10 power minus 9 to minus 3. Imagine there is a fan, there is a series, second fan, third fan, all are connected like this. And imagine the room is shrunk like a circular room, like a typical cottage industry in Japan. So the diameter of the room is slightly more than the diameter of the fan with a small gap of the order of mean free path. Because at minus 2 torr mean free path is quite high. Even there is a gap, that fellow does not understand there is a gap. It is like opening a door which is less than the size of your body. Even if it is open, you cannot go. So it is like that mean free path at that minus 2 torr already created by rotary pump. It is so small, high, that even a small gap is maintained between the container. In this case, it is the stator, the body, which is the house, and the fan. In this case, it is the turbine. So then what will happen? Suppose in this fan, I keep on reducing the dimension of the room till it almost touches, it does not touch. Then what will happen? Backside of that fan, I will get vacuum because it has thrown that air bottom and the air is not going. But in a room, what we want is air should come, give me aram, take my sweat, but again, same molecules will go and it is a continuous effect like this, circulation. Whereas, so imagine a fan is rotating, room is so small, it is almost touching the fan, then what will happen? You won't get wind. Because vacuum is there, there is no air. That back air is pushed. There is no air because our air has been removed. That is called turbomolecular pump. But you cannot one stroke you do it in the compression. 10 power minus 9 torr we want. We are not interested in giving velocity. We are interested in giving velocity and convert into pressure slowly, slowly. So in a small compression ratio of 5 for one stage of rotor and stator, such stages, 9 stages will be there with necessary bearings, etc., precautions, precision manufacturing. Then you end up into this turbomolecular pump. Okay. So all of you please read this alternative things, and just after 1.5 to 2 minutes I will give you. This slide is a very important slide, and this is the costliest pump. And if you are a mechanical engineer or electrical engineer, if you are taken employed in running, maintaining the ambience, not the clean room ambience is for the operators. This is the actual semiconductor manufacturer. Then you will have to see this properly. So please, I will give you 1.5 minutes. Go through the notes, go through the slide, and the blue looking things are connected to the shaft, and the red looking things are connected to the body like a donuts. And there is a top centering portion, there is a magnetic bearing, bottom there is a wick bearing, there is an induction motor in the bottom, and all of them is on the poor side. So what will happen when all of them are pushed? They come to the minus 1 torr now. Now the rotary pumping speed has fallen to zero earlier. This rotary pump now can easily take it up. Because earlier it was not able to take because 10 power minus 2 torque. But turbomolecular pushing it, giving some extra pressure, now turbo rotary pump can easily take. Now is the animation of the uh, turbomolecular pump. Just to see that, and after that, go to that slide. First, see this. So there are front, this is the collection flange. It is connected to your chamber. Now, front side, that is high speed turbine. And in between two turbines, the black thing that is called stators, which is not very clear here. So alternatively, stators are supported from the body and the rotors are supported by the central shaft. So when it starts rotating, then molecules are pumped from this side to that side. This is the static structure of, this is my envelope. See how they are removed. These are stators. They are retainers between, because two stator, third stator, fourth stator, they have to be separated and they should be clicked to the body. Now send these things are rotors. Afterwards, some additional drag stage is added to this turbo stage because that is anyway viscous region. Here it is molecular region. So that viscous region also will be additional drag. All that is finally we have to create enough pressure so that it comes into the working range of the rotary pump. Okay, so this is the bottom, that shaft, how it is connected, to the motor, and then shaft seals and lubrication, wick bearing. In the bottom side, it's a -1 torque. Even if it is impure, doesn't matter. But in the top side, it is connected to semiconductor chamber. So there we are not allowing any impurity contamination. So all the precautions you have to take. That's why it is costly. Okay, 99.99% that fellow is taking. It is like a typical coolie in the station. He is carrying much more weight than you. You are carrying a small bag, but your salary is 1 lakh and his salary, his day-to-day life is very small. So it is not that, because the intelligent work is not there. See, high speed, this ultra high vacuum pumps, they are trying to reduce the molecules, not the gas anymore. So the nature of the work will be, payment will be different. That's why it is very costly. So see this animation and now go back to this. There are other animations also. I have not seen here. Actually, when the rotor rotates, I gave a wrong thing. But anyway, you can get series of animations in the net. If you go to the turbomolecular animation, if you have time, you can see that also. But otherwise, this you try to read it for 2 minutes, right side and left side, with the understanding that we are given. If each stage is 5 compression, if there are 9 stages, what is the total compression ratio? Can anybody tell? Open your this one and or even chart box. There are 9 sets of rotor and stator. Each one is velocity and then pressure. It has been converted. So that way P1, P2 is there. Compression ratio is there. If each stage is 5, compression ratio. If there are 9 stages, what is the compression ratio? Because in class, when I said, many people said 9 into 5. They said 45. No, it is 5 to the power of 9. That is, answer is given in the below the pump. 5 into 5 into 5 into 5. That pressure into 5. Okay, compression ratios. Okay, it is not the differences of the pressure drop. Force is related to pressure drop, but the compression, heat of compression is related to pressure ratio. All that is explained in thermodynamics. So please read this thoroughly. It gives you action and construction of a turbomolecular pump. I'll come back after a minute. Hope you have understood little bit. So, but anyway, there are very good animations, and you can go through it at your leisure. Otherwise, we can go to the next slide so that you will get a feel of it. So, turbomolecular pump, the pumping speed is constant up to 10 power minus 9 torque, because at higher pressures, if there is 10 power minus 3 torque, 1000 molecules are removed. If it is 1 liter, at 10 power minus 5 torr, if 10 molecules are removed, then also it is 1 liter. Because 1 liter contains 10 molecules at 10 power minus 7 torr. So that's why pumping speed looks like constant, liters per minute. But this liter at minus 9 torr is different, that liter at minus 3 torr is different. Because P is proportional to the density. Okay, that's why in people, instead of mass flow rates or work done, they don't bother about V into rho. Even PV also is a very good thermodynamic quantity. PV units. No? PV represents the work. Actually, when you get volumetric flow rate, when you multiply by the density, you will get mass flow rate. In higher pressures, it is customary to measure mass flow rates because you can measure grams per second. But in vacuum micrograms, how do you measure? So instead of rho dV by dt, you make P dV by dt, because P is proportional to rho anyway. So that's how there is a additional concept called throughput and all that I'm not going to explain. But instead of having rho dV by dt, you can call P dV by dt, which is called throughput. So difficulty vacuum pumps are also like that. So if you try to understand all that, you will get a feel of that. And how do you match the rotary pump with the turbo pump? Because whatever at that pressure, that multiplied by that volumetric power pumping speed should match at the exhaust of this turbomolecular high quality pump, has to be removed finally by the rotary pump up to the atmosphere. Turbo pump can only pump from 10 power minus 9 to minus 3. It is connected to semiconductor vacuum chamber, nice, minus 9 km, switch on the lithography, fine. But who will take care of this junk? Whatever has come minus 3 tar, it has to be further compressed up to 1000 millibar and throw it to the atmosphere outside the clean room. So where to keep this rotary pump? What is the connecting pipes? This is called, there is a backing requirement for this. Just like we throw our junk into a small dustbin. Morning the Kamali takes it and throws it into municipal. From there that municipal van comes and throws. Same thing is going all the way out of the city. Same thing here. The final destination is atmosphere. But I cannot do it, turbomolecular pump. I can only remove, I'm a fine fellow. I can remove from minus 9 to minus 3 tar. Afterwards, minus 3 to relay race, the rotary pump has to be backing this. So that way, rotary pump does two duties. Initially, it is evacuating chamber directly from atmosphere to minus 3 tar working pressure and makes it ready for the turbo pump. Later, it backs the turbomolecular pump. Whatever turbomolecular pump is finally compressing it to minus 2, which is the working range of this fellow, it is further helping it to take it. If it stops helping, then the accumulation takes place at the exhaust and the pressure builds up and the reverse flow will take place. So you will have to continuously scavenge the molecules at higher pressure in the viscous tail, in the lower pressure in the molecular tail. They are molecular pumps, these are viscous pumps. Okay. So this S1 P1, the pumping speed S1 of the turbo pump multiplied with the ultimate vacuum should be same as the S2 P2. What is S dV by dt? So P1 V1 is equal to P2 V2. Now P1 dV1 by dt should be equal to P2 dV2 by dt. The dV1 by dt is nothing but volumetric rates. So S1 P1 is equal to S2 P2. That's what is given there. So this is how the pumping speed variations you have to understand. Next slide, please. So these are the various applications. I don't have to explain why this is important. So I just ask you to go through 1 minute, read it all this. It has understood, we have understood the turbomolecular pump, rotary pump, in between connections, oil. Here there is no oil, no lubrication oil, etc. Then it will degas. It will outgas. It will provide additional molecules which will interfere with your silicon molecule because it is a hydrocarbon oil molecules. They are not allowed. They become an impurity. They will dope it. N-type becomes P-type. With all the fab design, it becomes a failure. So you cannot have any contamination. The very idea of 10 power minus 9 tar is to produce contamination free atmosphere. Now you are contaminating with the oil of the pump, not allowed. So there are dry pumps, and it's a dry pump, turbomolecular pump, which is the ultimate and the last stage of the ultra high vacuum. Please go through it for a minute before I switch over to the next topic. Okay. This is just an information that these are the applications, these are the limitations. And okay, even if you don't understand thoroughly, it's okay. But these are the typical applications relevant to the semiconductor application, where this turbomolecular pump pre-evacuation backed by a rotary pump is a necessity. Before that, you cannot start any manufacturing. Okay. So next slide, this next slide, please. These are various components, flanges, valves. See, gate valve is a bigger opening, throttle valves, flexible bellows, straight connections, elbows. These are all the small requirements. Just like Tailor has got not only the materials and cloths, they will have small buttons and wires and seals. They're all required to make your chambers, connecting pipes, and the electrical feed throughs, all of them are required to make the manufacturing of semiconducting materials. It's not just a material making, it is the device making. It has to do a certain operation 0, 1. Several lakhs of zeros and ones have to be done in high speed. So naturally, the precautions are also accordingly very fine precautions. Okay, next slide, please. So if you understood components, yesterday we have shown system design also. These are various couplings. See, you cannot make everything rigid box. There will be some wire, another pipe, two things have to be coupled. So there is a o-ring if it is a normal vacuum. Otherwise, there is a metal gasket. Right side metal gaskets are shown. Left, there top side, there are two couplings with a wire with a o-ring, and that o-ring is centered by a center ring, and nicely it sits between the two mating flanges, and then wing nut, that clamp, when you tighten, the 15-degree angle is there, but that clamp tapered surfaces. When you are tightening, so for some cos for 15 degrees force will be there as a sealing force, and the two flanges will be lightly pressed. You don't have to tighten like a high pressure cylinders, because the air will be pushing it anyway. You have to only align them and give a little bit of tightening. The air force is much more than what mechanical force that you can give, because on the both sides, inside vacuum, outside air, that air will anyway make it tight, seal. But you should not, you should only alignment is more important. When it goes to ultra high vacuum, small seals, even the o-rings, gaskets, they will degas. So instead of gaskets, you put a metal things. But metal is also metal, another also metal. There will be micron gaps. So it cannot be sealing. Rubber can do undulations, but metal cannot do it. What they do is they increase the thickness of the flange and make a fine blade type of structure machined on those two flanges. So in between that blade type of structure called con flat, this gasket is kept. When you are applying a huge pressure in the tightening, the pressure force per unit area on that sharp edge is crossing the yield stress of that copper, and copper will start yielding it and feeling like a seal material. But one time if you do it, you have to throw it. O-ring will take again regain its shape. Rubber gaskets, but metal gaskets cannot do that. All those precautions are required in ultra high vacuum. The fellows who finally high tech engineers who are paid very high salaries, and they have to look after all these precautions in the intercouplings, pumps, maintenances, chambers, degassing, bake it, heat it, and when you give signal yes, then only semiconductor fellows will come and start doing all that. Till that time, it is only the mechanical engineers, electrical engineers, and metallurgical engineers, and sealant fellows, chemical engineers. These people have to do it. And at that time, clean room, people are entering that time. They will start opening. They will put this wafer into that, and one by one into a rough vacuum first, then fine vacuum, all that and all. Yesterday we have explained. So that is called high level semiconductor manufacturing. Next slide, please. These are various walls, cross sections. I don't, it is like a bellow walls or diaphragm walls, gate walls. Each, whenever there is a motion, that motion also there will be leak. So you should have shaft seals. There are multiple shaft seals like this. And then couplings, there are ways to do it. Just like you have seals, whenever some water pump, there will be some drops of water coming out of old pipe in the wash basin. You will see some leakage. They are because that seal, the shaft seals are leaking. Same problems here. You have to take all that. There are bellow walls, there are butterfly walls, there are ball walls, there are gate walls, there are throttling walls sometimes, gas inlets, silane, various gases without spoiling the vacuum, but spoiling little bit. That means throttling, very small amount of gas is put for doing a purpose there. But when it is entering from the cylinder, there is a huge pressure drop. There is a throttling. Throttling is different from the shut-off valves. So there are various mechanisms you have to understand these things in a pneumatic language. Next slide, please. And magnetic seals, bellow walls, shafts, how they are coupled. Whatever you are trying to do the outside, the inside connection is given without any manual connection. Okay, you try to do something on bellow, bellow will be inside moving because of flexibility, but these two are pneumatically isolated, action and reaction, but the reaction takes place. There is an additional motion, tilt, rotation, X, Y, Z inside going on as per the outside, and there are magnetic couplings. There is a pipe, there is a magnet when it is moving inside, that iron piece also moves. So through that magnet, like a paper you keep bottom, if you put magnet motion, top fellow will move, but you are not physically touching. So such mechanisms have come like ferrofluid seals, etc. All that is explained here, but some other day you can read it in the net also. Next slide, please. With all these things, when pipes are connected, walls are connected, flanges are connected, electrical feed-throughs are given, baked and clean room, people have entered, -2 torr, -9 torr, then only things will come, they will switch on. But -9 torr is not coming. Turbo pump is running, rotary pump is running. Last minute, the space mission stopped because hydrogen supply is not going. Then such checkpoints are required here also. Unless vacuum is there, the semiconducting experts, fab design people have no role to play. They cannot start anything. If silicon vapor stays like a silicon vapor, there is no PN junctions, there is no transistors, there is no interconnect, there is nothing. After getting good vacuum, it goes inside through the load lock chamber. Then you do whatever operations. If operation theater is not clear, doctor will not come. So same thing here. If vacuum is not coming, what to do? An experienced person can feel that. So pump is not running properly. That's why vacuum is not coming. Gauge is not reading properly. Actually, vacuum came, but gauge is not reading. The instrument which is reading the vacuum, that meter is not reading properly. But vacuum is there. That is second thing. The third thing is there is a lot of leak somewhere. I have not tightened. It is going. It is like not properly closing the wall tube of a rubber after putting the pressure inside the tire. Slowly after 5 minutes, no pressure because it has leaked. It is the positive pressure means inside to outside, but in vacuum, outside to inside. Air is a higher pressure compared to the vacuum. So whenever you are switching on a curve, you see there, whenever you are evacuating, it comes to the ultimate of the vacuum. Then if you isolate the pump, if it is a perfect system, it should stay at that vacuum, but pressure will rise. Because of unidentified rings, somewhere some fine leaks, or some vapor pressures coming from the surfaces of the chamber, or some water vapor evaporating inside, they are called virtual leaks. They are not leaking from the atmosphere. They are inside chore. It's like somebody is every day you are losing 1 rupee, but
The household Kamali has not come. So who has taken? Some inside fellow. So that is like the outgassing, degassing is an internal chore. Whereas a leak, permeation, diffusion through the walls from the outside, they are external leaks. So whatever be the thing, if it is an internal leak, it goes up to some time when the saturated vapor pressure reached, it will not further degas, so it will go up and stabilize. This is called stethoscope of whether the leak is outgassing type or whether it is a real leak. How to do that? First evacuate it, isolate the pumps. You have not come to the semiconductor manufacturing. First, there is some problem now. You have to identify. You have to solve it. You get the vacuum. Then only come ask them to come. So during that time, what you do is you switch on the pumps. Instead of minus 9 tar, it came minus 7 tar. There is some leak. But isolate that pump and see the pressure rise curves. If pressure is linearly rising, then it is leak. If it is non-linearly rising, that is called degassing. If it is non-linear initially and then linear, then it's both. So from the pressure rise curves, you can understand whether the problem, which is the fundamental for you to solve. Otherwise, 100 days, the semiconductor manufacturing facility will be closed unless you solve and get minus 9 tau. Now, sometimes you have solved such a fine leak. Pumps are continuously running. You are not isolated. So it doesn't matter. If the salary is too high, kharcha can be high, doesn't matter. But salary is low, when kharcha is more, then you have to careful. So when the leak rate is tolerable or not tolerable, you also get sometimes heat, sickness, but you don't go to the doctor. But if it goes to intolerable, you go to the doctor. So that's called first identify whether there is a leak or whether there is outgassing or both, and whether they are tolerable or not. If it is a very large chamber, very small leak, then nothing, don't worry. If your salary is 10 lakhs per month, every day some 10 rupees is going, some chore is happening inside, you don't bother. If your salary is 100 rupees and 10 rupees going, you have to bother. Okay, so if the chamber is a bulb evacuation industries, they have to worry. Bulb is also evacuated bulb. But because volume is small, same amount of small pinhole will increase the pressure within 10 days and filament gets burnt the moment you switch on. That's how most of the olden days bulbs get burnt very fast. Philips company used to be there because vacuum sealing is very good. It used to stay for a year. When it goes to larger chambers like TV tubes or semiconductor chambers, same hole, the air is leaking because of pressure drop, but inside after going, it is huge volume. Pressure burst is not much. It is like big tub and a small beaker. Both are having same 1 drop per cc per second. The level in the glass will fall very fast. The level in the tub will not fall at all. The same thing here. So it all depends on the leak rate, that is V dp by dt, pressure rise rate, is exactly equal to the throughput, that is pumping speed created by the pump. Then it is okay. If the small leak rate is compensated by continuous pumping, you don't bother about it. But if it is in spite of pumps running, pressure is rising, then you'll have to bother. So that's where these things are given, virtual leaks, leak rates, etc. You just go through it for a minute, this slide, I'll come back. I'll finish it another 15, 20 minutes.
Hope you have understood this. Okay. Then next slide, please. Supposing it is intolerable, what to do? But you don't know where is the leak. Somewhere there is. You need a stethoscope. Doctor only can do it. You cannot do it. You are getting fever. Fever can be because of any reason. But doctor will identify by putting all these things here and there and then check or you ask you to open this, that, and whether you are feeling hungry. After all these symptoms, he will find out where is the problem. Same thing in a vacuum chamber. If like vacuum is not coming, and if you are not intelligent, of course, most of you are very intelligent, no doubt about it. But otherwise, you end up in a wrong route and you create another problem. If a doctor is a bad doctor, instead of solving the problem, he will give you such a medicine, it will create another trouble. You are not supposed to do that. So what you should do? You should first identify pressure rise rates and see what is the thing, whether it is a leak checking, degassing. If it is only degassing, just bake the chamber and then you remove all that with a rough pump and later forget about that pump and baking is done. Now when you firstly evacuate with a good pumps, it will come. Okay, but first there are some simple methods for leak checking. Leak checking means leak locating. I know that somewhere there is a leak. But where is that? It can be in some welded junction, it can be some connection point, or the chamber connection, or some feed through is broken, but spine break, we cannot see that. Now what to do? So all the you run the vacuum pump, suspected places, you put some small spray of non-air. Air is nitrogen oxygen. You try to put something which is other than air. Now, wherever, if you are luckily happen to be there nearer to that leak, means earlier nitrogen molecules are leaking. Now these argon molecules will leak. Then what will happen? The vacuum gauge is calibrated for the nitrogen. The calibration chart has changed because now earlier also it was leaking. Now also it is leaking. Earlier nitrogen was leaking. Now it is argon was leaking. Immediately pressure shows as if like the burst. Pressure has not changed, but the sensitivity of this gauge to the new molecules which are leaking from the outside, that has changed. Now that pressure burst shows that that spot there is a leak. So, and like that you have to do some fine leak checks. These are simple methods of leak checking. In the high vacuum side, you can use high vacuum gauge, otherwise normal gauge. Even very gross leaks, you don't need any of this vacuum. Instead of vacuum, you pressurize it like a puncture testing. What they do puncture testing? They put some pressure and then put it in the water. Wherever there is a leak, bubbles will come. Then they remove it, then close it and paste it. Is it not? Same thing we have to do it, bubble test. And if bubble size is not much, instead of water, we put soap solution. Soap has got a surface tension. For the same amount of air coming out, the bubble size will be bigger for you to see that. All this chemical engineering, chemistry, you should know. But if you put a soap solution, you are impurifying the joints. Sometimes when you put something, it may be closing. It may be closing the leak. So you are not, since you are solid or you thought, but actually instead of leak checking, it may close because of surface tension effects. So you will have to be very careful. Wet tests are not good. Dry tests are very better. So sometimes how to do that dry test? Very fine leaks. All these leak testing, small rough mechanisms are not working. Then you go for a commercial leak detector. Next slide, please. This is the last slide. Last but one. So this is the thing. The system which is connected to a vacuum pump. Okay. Jack, can you make this left side figure a little bigger?
Actually, I'm not able to
Okay,
zoom
forget
the
about it.
picture.
So when the pump is connected, you try to spray some gas, and along with your chamber and pump, there is one mass spectrometric leak detector, which is a partial pressure gauge basically. That is mass spectrometer. And
when you are throwing with the helium gas, because helium is very less in the background ambient. Only when you put some helium in the suspected areas of leak, you try to immediately get a pressure rise. It's not the pressure rise because the leak detector, which is a partial pressure gauge, it is calibrated and locked for helium mass. Okay, when normally air is leaking, it will show like a very high vacuum. But when the helium is sprayed, it will suddenly show high thing. There is another total pressure gauge which is measuring the vacuum. But here there is, in addition to vacuum gauge, you put a mass spectrometric gauge, which is also a vacuum gauge, but this is a partial pressure vacuum gauge. Within that vacuum of 10 power minus 9 torr, there is nitrogen, there is R. So you are measuring, you are making the gas sensitive to only one particular gas. If you do that, like barium test, when you do it, how the barium goes into the lungs, from there they will find out if there is a problem at all. Same thing here also, leak checking. So particular gas which is not there otherwise in the ambience, when you try to spray, that will go into that. Such a fine leak detector, the mass spectrometric, it is a basically mass spectrometer. It is tuned to the helium. How, what is that mass spectrometer? Electrical engineering, if you are interested, if they give time, I can explain. Otherwise, you think that it is tuned partial pressure case. Next slide, please. So this is how typically a mass spectrometric leak detector looks like. So it is basically all the ions are coming, but it is sensitive to only particular thing. So particular helium ion with electric and magnetic fields is made to bend. That bending radius is proportional to the mass to the charge ratio. So whether it is a quadrupole or this magnet deflection magnetometer, you use these electrical and magnetic fields in the ions which are leaking atoms and see to that they are projected onto a detector and you try to get a detection of the leak. Once you identify the leaks, then close the leak by sealing it with some araldite or something. Then once all these things are there, first identify the problem. Just like when you go to the doctor, he will first do the diagnosis. He will write that test, this test, this test. Then only he will give medicine. So once you identify where is the leaks, and provided you are completely checked all the leaks. If there are two leaks, one on top and one on bottom, by chance you are measuring the leak here and there is no leak there, but leak is here, but helium is light in the thing, it goes and leaks. So you are immediately getting a signal, sound alarm will come. So you are thinking there is a leak, but actually leak is there. So always leak test is from top to bottom, not from bottom to top. There are many hints in the leak detection. You have to go through it. Why helium? Because helium is not available here. So it will act like a tracer gas. And helium is a molecular weight is small. Even through fine holes, it can be going and it will give you a signal that something wrong here. There is a hole, there is a puncture, there is a crack, there is a welded joint problem. It will tell. So if you do all that things, and finally, whether problem is solved, even then it's not solved. You get vacuum, but it's a bad vacuum, -8 torr, but it has got oxygen. So there is one residual gas analyzer that is also mass spectrometrically detected, where one first minute oxygen partial pressure, next minute nitrogen oxygen pressure. It is a chemical analysis of the residual gas. If you lock it, it becomes leak detector. If you don't lock it, it becomes a gas analyzer. So both these things are essential accessories connected in addition to scanning electron microscope and in addition to background pumps on the electrical things, semiconductor and gases. All these things together will form that semiconductor manufacturing hub with continuous pumps running, vacuum pumps, with continuous electrical signals going on, with leak testing going on, and analysis going on, and vapors are entering, lithography, various systems are taking place. So parallelly you have to do it. Data is too much. If you want to handle data and analyze it, you require AI algorithms. So it goes like that. Just now he explained, no? So that's how it is. But first of all, how do you design it? First one, this cross-linking, this transistor is connected to that transistor. Two transistors together is connected to another resistor. Like that, 1 lakh such combinations. That is called fab design. So this, they try to do it in the just now 1 hour before he has explaining, no? That design simulation, they do it. Whether it is really happening or not, testing fellows will do it. So like that, they will continuously, there will be auditors. They will be doing their work. So the whole team of it will make finally a chip manufacturing. Next slide, please. So I hope you have got some idea of rotary vane pump, turbomolecular pump, and leak detection, components, etc. Well, you have got only vocabulary, you have got only terminology. I don't think you have fully understood, nor I could make you understand. It's not possible because it is a one semester course. So naturally it takes time. You have to read some books, okay, independently at your leisure, at your pleasure. You should read in the Saturday, Sundays. Now, instead of looking at cell phones or some other things, you should have a passion to understand the subject and read it continuously in the weekends. That weekend will be very strong end for you, I'm telling you. So with this, I thank you very much for giving me this opportunity. If you have any doubts, I have no problem. Let us try to discuss. I don't think whether I can answer or not, but we can discuss.
We now invite participants to post their questions for Sir in the chat box.
A few selected questions will be taken up for discussion. Sir, there's one question in the chat box. Can any human being allowed inside a vacuum chamber? If so, how to survive?
Very good question. Human beings contain blood. Human beings contain skin. I think yesterday's lecture he has not attended, day before yesterday. There was a clean room lectures. Even hair will create lots of impurities. If there is a one hair left, I told you today also, one drop of sweat, if it is inside, by chance before cleaning it, that's it. It will take 1 month to junk. So if a human being goes, there are two things happen. First of all your liquids, whatever these things, they will evaporate under a vacuum because the saturated vapor pressure is much more compared to the actual pressure existing. So it wants to saturate the chamber, so it will evaporate continuously. So you will get dehydration immediately. And then because of pressure drop, inside blood pressure is 1000 millibar and outside 10 power minus 2 thing, all the 9 to 10 openings of your human body will explode, blood will come out. I have done one project from a Bangalore company long back. What is the time for killing if a man enters into vacuum? It was coming out to be 20 milliseconds or so. Supposing when you are flying at 10 kilometers height, what is the typical height of it? What is that? Plane, passenger flight? 10 kilometers. You know that? Why it is 10 kilometers? Because vacuum is created, it's only 76 star. So without any friction, it is going at 600 kilometers. Then if it is so, why not 30 kilometers? Then it is still less. That's how rockets are going. No. If you go to the 30 kilometers, it can go in vertical direction with Newton's third law, like a rocket principle, not the cruising flight. Cruising flight requires Bernoulli's principle. The air must be there. The air velocity should be less and velocity should be more on the top and less here. So velocity energy is reduced, pressure energy is more, lift force, drag force, thrust force, friction force. These four forces will be balanced at 10 kilometers. If it is anything more than that or less than that, one of it will dominate. So cruising is not possible. So most of the time, the safest way is to travel at 10 kilometers. Now, anyway, now at that time, if there is a window broken, a small kid is breaking the window, the outside is vacuum. It is exactly the question that you are asking. Infinite volume vacuum. Immediately within few seconds, all the blood will come out of the body. Okay. It is just open the door of a window of a plane. You will know the fact. Same thing here. In fact, if you are entering inside, you will never get vacuum at all because you are degassing so much moisture, etc. Pumps will say, forget about it. So it's good. If they start working and producing vacuum, you will die. Okay.
So there's one more
Is it clear?
How can we know if these vacuum pumps are malfunctioning?
Yes. If it's a rotary pump, if it is malfunctioning, you will get hear the sound also. You can feel it. That are very experts can understand very fast. What you do is you try to keep walls here and there and close that walls and keep gauges. Isolated pump, only on the pump if you put the gauge, is it producing vacuum? Then next stage that put. So stage by stage, if you are coming, only when the chamber is connected, vacuum is not coming. Then it's not the fault of the pump. It is the fault of the chamber leak. Whereas, whenever chamber is connected,
If even without chamber connected also, blind also it is not coming pump, then pump is the problem. Okay, and that is one way. Then pump is running, but it's not running its full potential. Okay, that will happen because instead of minus 2 torr, 10 power minus 2 torr, rotary pump has get minus 1 torr. Instead of 10 power minus 9 torr, turbo pump has given minus 6 torr. Why? Because somewhere the number of revolutions is not much. There is a sensor, RPM level, it can be, there will be a board for the breadboard. There is a display system is there. Display immediately shows. From there you can correlate it. This is the typical error analysis of a computer type. Same thing story here. You can understand a turbo molecular pump not running means what? The speed of the rotor instead of 80,000 RPM, it is 10,000 RPM. Immediately you can see that RPM sensor. Or else if it is heavily leaking, then thrust is so high that air is coming, so turbine is becoming, braking force is there on turbine. Instead of molecules entering and removing for the vacuum purpose, there is a leaky huge air is breaking it. That's what is happening when the plane is landing. Immediately you will open, the wings are opened. Why? Because the pressure energy, velocity energy not converted. Huge amount of brake force is applied. Is it not? So that sort of thing will happen here also. Whatever is happening to the aeronautical things, same thing here. Okay, pressures, it is basically aero problem. But when it goes to the higher side, it is a molecular problem. And the rotor, all these rocket engines, after 10 kilometers, it is a perfect ultra high vacuum. So you require a thrust, second stage, third stage. Otherwise, you will not go. That is a Newton's third law principle. But here it is a Bernoulli's principle. So pumps are not working, or electrical wire. If a rotary pump sometimes will work reverse, it becomes a compressor with a capacitor properly not connected, because the rotor rotates in the reverse direction. The inlet becomes exhaust. That is another problem. And even if things are there, one valve is automatic valves are not opened, vacuum is not coming, but you think pump is not running, you throw that. So wrong decisions are always taken because of less knowledge or less skill or less experience. Sometimes it creates much more delay in the operation. So pumps
Sir,
not
one more
working is
question.
very easy to understand.
Sir, how do modern magnetic bearing turbomolecular pumps improve vibration control and contamination-free operation compared to conventional bearing systems?
Yeah, conventional bearing systems are oil lubricated, these things. Magnetic, high-speed magnetic bearings are so perfect. There is on the spindle of it, there is one circular magnets, and in the another casings which is concentric to that, which is not touching to the rotor, there are some additional ring type of magnets. And in addition, there is a emergency ball bearing will be there, which is not operative in the top side. In the bottom side, there is a wick bearings that will take the thrust and huge amount of mass or whatever that feeling. And these turbines are not allowed to tilt. If it tilts, no, the rotor blades will touch the stator blades. Then it becomes a grinder. So that bearing action has to be perfect. And the magnetic bearings are very high powerful magnets. Only under the high speed rotation, the dynamic balancing will take place. And if there is the fellow wants to go to this side, immediately push will come that side. So very high speed reaction forces will come. They try to maintain that. And high speed, that's why whenever there is a levitated train, when it is running, it is very easy to control. Otherwise, when it is slowing down, it is very difficult to slowly make it down. So same thing here also. When it is running condition, there is no problem. When it is a pickup of the running, then when it is slowing down or when you switch off the things, that's where the problems normally come. So you have to be careful. That's why you should not break the turbine at high speed from the axial way. You should break it tangentially. So lights like right side, you have to, on the periphery side, you have to let in some air in a controlled manner. And if necessary, if there is a power cut, turbine will rotate continuously for half an hour because there is nothing to stop, because there is hardly any vacuum. There is nobody, magnetic bearings. So if you want to stop, you have to put some air through a leak, and that should not be normally kept. So there is an automatic thing reaching that gets electrical power. There is a valve, electropneumatic valve, that gets electrical power from this turbine only. The turbine will act like a generator. The motor would lost its electrical power, but the armature becomes now the field coil. That automatically from the motor becomes a generator. This motor and generator basically rotating machines only. Now, when that flux cutting is there, the output, instead of applying the force from the electrical signal, that magnet is rotating, so output voltage can be applied to this gate of that pneumatic valves. This is a self-contained venting of it, slowly safe operation. But in your question is, the bearings are so strong, there is not even small tilt which is not allowed. That type of bearings have come now. That's why it is very costly.
Sir, I think
So
we have
these were
taken,
all the
sir, you have taken
questions.
all the questions. So thank you, sir, for continuing this discussion and deepening our understanding with new perspectives and advanced concepts.
Your session added significant value by connecting theoretical principles with practical applications. We sincerely appreciate your time and guidance. And before we conclude today's sessions, we request all the participants to kindly fill out the feedback form for this session that has been shared in the chat box.
We
Thank you,
thank our
sir.
esteemed speakers.
Once again, thank you,
Yes,
sir, on behalf of the
Thank
Department
you
of
very much.
Multidisciplinary Engineering and taking out time. Thank you once again. The session was very useful. We
It's my
hope that
pleasure, but when we are putting too many concepts in one small period, there will be jamming, but you cannot avoid it. Just because jam, you don't stop journeys.
yes, sir, definitely. Thank you once again.
Uh, Okay,
I think
so
we can close
they can
the
go through
today's
my
session.
NPTEL slides. Each is explained, each pump is explained for 1 hour.
Yes,
So there
yes,
you
yes.
can
I
go
hope
through it.
everybody has noted down the NPTEL reference sir has given to us in yesterday's session also.
So slowly go through it. And even the term troubleshooting, etc., there are many electromechanical things.
And sir has been very active in delivering sessions on vacuum technology. We also had this opportunity to attend one of his sessions at IIT Delhi, wherein we first interacted with him, and since then he has been a continuous source of support to us and to our department and institute. Really thankful, sir.
Thank you very much. I enjoy. Uh,
Okay,
Very
sir.
good.
I think
So all of you have a nice weekend. And of course, tomorrow there are again sessions. So, but
yes, sir.
there will not be more of vacuum, but there will be full of high pressures.
Of course, sir. They are going to be more of on VLSI design and industry. Some
So
other industry experts are there.
yeah, it's coming up in a very big manner, semiconductor manufacturing. Please see to that you understand all these points and go through all these lectures, and they are very nicely organizing these events. And if you understand, if you are quite passionate, I have I can put a joke that there will be one more zero on the right side of your salary.
Definitely, sir. Thanks once again, and good night, sir. Good night to all
Good
the
night.
participants. Yeah, good night.
Thank you very much.
Thank you, sir. Thank you.
thank you, sir.